First of all, I thank for the scientific committee to give me the opportunity to talk here. Okay, today what I'm gonna talk is about the torsion of cohomology of real toric manifolds. First of all, I will briefly give the definition of the quasitoric manifolds and small covers. So a quasitoric manifold M of the dimension 2n is a manifold M with an effective action of the n torus, which is locally standard. Locally standard means the action locally looks like the standard n torus action on the n-dimensional complex space. And the orbit space should be diffeomorphic to a simple polytope. This is the definition. Actually, I think most of you already know the definition. And similarly, a small cover is defined, but its dimension n is n. Its action is z mod 2 to the n. So a toric manifold is a non-singular complete toric variety, and a real toric manifold is the real locus of a toric manifold. So quasitoric manifolds and small covers can be viewed as topological analogs of toric manifolds and real toric manifolds, respectively. So in this talk, I will barely distinguish quasitoric manifold and toric manifold and real toric manifolds and small covers. So the cohomology ring of a quasitoric manifold over the integral coefficient is very beautifully described by Danilov and Jurkiewicz for the toric case, or Davis-Januszkiewicz for the quasitoric case. But for a real toric manifold or a small cover, there are no such results for the integral coefficient. So there are some partial results only. So in the original work of Davis-Januszkiewicz, there were only mod 2 coefficient structure, and relatively recently, the group structure over the rational coefficient was found by Sushu and Trevisan. And inspired of their work, my collaborator Su-young and me found a ring structure over the rational coefficient or the mod Q coefficient when the Q is an odd number. And actually, I think the Z mod Q result can also be obtained by Sushu-Trevisan's way, but their method and our method are very different. And our method can describe the cup product structure on the cohomology. So this is somewhat ultimate question, but for a small cover M or a real toric manifold, would it be possible to describe the integral coefficient of the cohomology ring or group over the Z? So for a small cover M, we already know the cohomology for the coefficient Q, mod 2 and mod Q for odd numbers Q. So as direct applications of the universal coefficient theorem, we can know in most cases the cohomology ring should have many two torsions. For example, real projective plane RP2 or the Klein-Bartel, they have two torsions, as you know. And once one computes mod 4, mod 8, mod 16, etc. cohomology, then we could compute the integral cohomology as the group. And since now we know the ZQ coefficient for Q, odd number Q, so we have a tool for hunt for all torsions of the integral cohomology of the small cover. So the goal of this talk is to answer the following question affirmatively. So we are gonna find an explicit example of a small cover which contains an odd torsion. And the following question is still open. Is there a small cover such that whose cohomology ring contains a 4 torsion or 8 torsion or 16 torsion and so on? It is still open. So to find such an example, we introduce one interesting class of Delson polytope. So a building set B on the vertex set 1, 2, blah blah n plus 1 is defined to a set of non-empty subsets of the vertex set such that first of all the building set should contain every singleton 1, 2, blah blah n plus 1. The second condition is if B has two elements I and J which intersects, then the union, then the B also contains the union. For example, consider this set. So this set, this notation should contains very many braces, so I just prepare this notation. So for the first condition, it just contains 1, 2, 3, and 4, so it contains all singletons. And if its two elements 1, 2, and 2, 3, 4, they intersect, so their union 1, 2, 3, 4 is also an element of B. And next we define a graphical building set. Let G be a finite simple graph of the vertex set n plus 1. Then a graphical building set B of G is defined to be the collection of subsets of n plus 1 such that the induced subgraph of G on I is a connected graph. So if the graph is the path graph 1, 2, 3, 4, then for example, the induced subgraph 1, 2 is connected. So the B of G contains the element 1, 2. Okay? And for example, for another example, the graph 2, 4 is not connected. So it doesn't contain the element 1, 2, 4. Yes? And one can easily check this graphical building set is indeed a building set. So this Minkowski sum is easy but the technical notion for this talk. For what you really should know is that any building set defines a simple polytope called the Nestohedron. It is defined by the Minkowski sum, but it is somewhat technical. And if B is a graphical building set, then the corresponding simple polytope is called a graph associahedron. I think Mio gave a talk related to a graph associahedron. So a theorem of Zalabinsky says that every Nestohedron is a Dalzang polytope. Furthermore, there is a natural way to obtain the Nestohedron by truncating the simplex. So one can obtain every Nestohedron by starting a simplex and cutting its edges. So and additionally, since every Nestohedron is a Dalzang polytope, for given a building set, you obtain a projective toric manifold or its real locus, which is a small cover or a real toric manifold, right? So let me see an example. This is an example you saw in the previous pages. So to construct a Nestohedron for this building set, we start from the three simplex, which has the 4 facets, and you label each facet from 1, 2, 3, 4. Then every face of this simplex has the corresponding name. For example, this edge has the name 2, 3, since it's the intersection of the facet 2 and facet 3, and so on. This is 2, 3, 4, and so on. To obtain the Nestohedron, you cut the faces corresponding the elements of the building set, except the entire set. For example, you cut 1, 2, 2, 3, 3, 4, 1, 2, 3, and 2, 3, 4. Then you obtain the resulting polytope. So P of B is as I said, P of B is a Dalzang polytope, and it has the corresponding real toric manifold, which is called the canonical real toric manifold of the building set B, and we denote by M of B. And since it is a polytope, it should be a small cover. So one of our theorem is that if B is a graphical building set, then its corresponding small cover has no torsion on its cohomology. And furthermore, the Betti numbers can be combinatorially described in terms of the graph G. So the Betti numbers are very deeply related to the so-called A number of G. So to construct our goal, let K be any simplicial complex with vertex set V of K. So we define a subset of the vertex set is a minimal non-phase of K. If sigma itself is not a phase of K, but every proper subset of sigma is a phase of K. So we denote by Mn, it is for minimal non-phase of K, the set of such minimal non-phases. And B of K is the minimal building set, which includes every minimal non-phases. So let us see an example. Let K be defined, let K be a simplicial complex given by this. Then minimal non-phases are 1, 2, 1, 3. They are all not phases. 1, 2, 1, 3, 1, 4, and 2, 3, 4. So B of K should contain every minimal non-phases, so it contains the red elements, and by the condition 1, it should contain every singleton, and by the condition 2, if, for example, the element 1, 2, and 1, 3 intersects, so it also contains the union of 1, 2, and 1, 3, so it contains 1, 2, 3, and so on. So we shall see some pictures. So let us start from the simplex. Oops. So this is a Schlegel diagram of P of B. So we should cut all these faces of the simplex. So from starting from this, we cut 1, 2, 1, 3, 2, 1, 4, 2, 3, 4, and so on. If we only cut 1, 2, 1, 3, 1, 4, 2, 3, 4, then we get the original version of Bossio and Mielzmann's construction to show that to show that there are arbitrarily many moment and complexes to moment-angle manifolds, which includes a torsion. But for our objective, we cut additional elements. Then this yellow region is for next page. So now we present the Susu-Trevisan and Che-Park's formula to compute the cohomology of small curves for rational and mode Q coefficients. It is very similar to the Hochster formula, but in Hochster formula case, we consider any subsets of the set of facets of P, but in small cover case, we only consider the set S of lambda. S of lambda is a set of subsets of the set of facets of P determined by the characteristic map lambda. So the problem is the problem is, if M is the canonical real toric manifold given by Bk, then we have P of sigma for some sigma, but in general, sigma is not an element of S of lambda.
Here, isomorphism is just as a group is not the ring.
This is just a group isomorphism.
There's some isomorphism to rings.
Yeah. Yes. Yeah.
This formula itself is just as a group isomorphism, but we can give algebra structure.
So, okay. So our objective is to find the small cover which has an odd torsion. So we will pick a simplicial complex K which has a Q torsion, but in this case the sigma is not S of lambda, so P sub sigma is not a summand of the cohomology of the small cover in this case, but we can do it by doubling the building set. The doubling is defined by this. So if a building set is given by this, then you just doubles the singleton, the every singleton, and you double every element of every non-singleton elements by this way. Then you can very easily check this is indeed a building set. And actually, this double is actually given by the double of the simplicial complex K. So the double of a simplicial complex is obtained by multiple simplicial wedge construction on each vertex of K. So then every minimum non-face is doubled, but I omit that. And so pick K so that its cohomology, its simplicial cohomology, contains a Q torsion for odd Q. For example, the mod Q Moore space. You can pick any such K. Then our main result is the small cover or real toric manifold dot MBK prime, which is also a real toric manifold, contains a Q torsion in its cohomology. So since the double is simplicial wedge operation is topologically just a suspension. Suspension just shifts the cohomology in 1 degree, so it preserves the torsion. And if K prime is the double, then the yellow region in previous slide is just homotopy equivalent to K prime, and it is indeed in S of lambda. So Sushil-Trevisan-Che-Pak formula guarantees the Q torsion part is indeed the summand of the cohomology. For rational or Z mod Q coefficient, then the universal coefficient theorem completes the proof. Okay, this is the end of the talk. Thank you for listening.